Okay, in order to solve the next example question, we need to see one more property, and that's quite a critical one as well. What was it? The eighth property or something like that. It's differentiation in time property, you can call it like that. If you have this kind of a situation, y of t is equal to d by dt of x of t. Notice that as long as the signals are nicely behaving, their derivatives will have the same period. For example, what's the derivative of a cosine? The derivative of a cosine is a sine. And cosine has the same frequency as the sine, its derivative. So by differentiation, the periods don't change. It will still be a same or similar periodic signal. But of course, for some signals which are not continuous, then the derivatives will be a little bit problematic. We will have to handle that. But for the general case, the situation is as follows. If you have a derivative of a signal, and suppose that x of t has Fourier transforms AKs, then its derivative, y of t, will have Fourier series coefficients in this form: j, k, omega 0, ak. So you will have to multiply it with j, k, omega 0. Interesting property. This property could again easily be proven by the expression, the Fourier series coefficient, or the Fourier series sum formula. Take the derivative of that summation formula. You will see that the exponential e to the jk omega 0 t was in the exponent, right? So that exponent will come down with jk omega 0 times ak times e to the jk omega 0. So it's an easy property, as simple as this one, but it's very helpful to solve some of the questions. By the way, the opposite is also true except for k is equal to 0, of course. By the opposite, what I mean is this. If z of t is the integral from minus infinity to t x of tau d tau, which is the accumulation, that corresponds to the opposite operation of the derivative at the top, then z of t will have Fourier series coefficients ck, that is equal to 1 over jk omega 0 times ak, of course for k different than 0, because as you see now k is in the denominator, which imposes a danger for the case of k is equal to 0. It must be handled separately. But one of them is, for the derivative you multiply by jk omega 0. For the integral you divide by jk omega 0 in general. Now using this property, the next example is this. A strange signal, again very simple looking but infinitely more complicated as opposed to the rectangular pulses. This is a triangular pulse. Like this. And let's call this thing y of t. Okay. And the labels are here. It is 2 and it is 4 and 6. So and here you need an 8. So what is the period for that? The period is 4. Now the question is this: can you think of the derivative of this thing, which would correspond to the integral of the other one? What is the derivative of y of t? Of course, we need to find the Fourier series coefficients. Let's say EKs are what? That is the question. Now let's take a look at the derivative of y. Let's call it y prime of t. What is that? It is, by the way, I must put a label here. It is 1. So the slope up to 2 is 1 over 2. And then from 2 to 4, it is minus 1 over 2. And then it becomes a 1 over 2 again. And then after 6, it becomes minus 1 over 2 again. And at the left hand side, it is going on as well. Look at that. Do you remember this? Do you remember this signal? That signal is the previous question, which we called g of t. So we already know the answer to g of t. The Fourier series coefficients are coming from there. So y prime of t is equal to g of t, and its Fourier series coefficients were already there. What was that? It was sine. It was e to the minus j k pi over 2 times sine pi k over 2 divided by pi k. What? Sorry. Go away. Pi k. Then from here, what are we going to do now in order to find the Fourier series coefficients of the top shape? The bottom is the derivative, the top one is therefore its integral. For the integral, what were we doing? We were multiplying by 1 over jk omega 0. We were dividing by jk omega 0 in the words. So that's what we need to do. Quite simply, we say that y of t has Fourier series coefficients ek, which are equal to 1 over j pi k, no, there's no pi, jk omega 0, excuse me, k omega 0. What is omega 0 here? Omega 0 is pi over 2. 2 pi over 4, in other words, the period is 4. So jk pi over 2 times 1 over pi k. I'm going to write the denominator of this, the extra terms right now, and then I am going to put what is going on. I'm unable to write. E to the minus jk pi over 2 times sine pi k over 2. Let's try to simplify that. We will have 2 pi terms multiplying in the denominator, 2 k terms. So we have pi square, k square. And what else do we have? We have a 1 over j in the denominator. That's also okay. So this over 2 comes to the numerator. 2 over j k square pi square e to the minus j k pi over 2 times sine pi k over 2. And these are EKs except for k is equal to 0. So k must be different than 0 for this thing to hold. For k is equal to 0, you have to find the case or the BC coefficient of this thing. And for that, I guess you can do that just by looking at the area underneath. It is 1 over 4, 1 over t times the area under one period. What's the area under one period? The width is 4 and the height is 1 of a triangle. Therefore, it is 2 as an area. And the period is 4, so it is 1 over 4 times 2. And we say that E0 is equal to 1 over 4 times 2, that is 1 over 2. So separately you need to indicate the DC coefficient. For 0, it is 1 over 2. For all other case, ek is equal to that long term over there. And without using the properties, trust me, you will not be able to find it using the integral formula of the Fourier series coefficient. It's very difficult. So you need these properties. Of course, I promise that the questions that you will encounter will always be available through some properties. So it won't be very difficult. If there is no property, then it means the integral is manageable. It's a very easy thing. Or otherwise, it will be requiring some properties. But you will have to guess by inspection which property is appropriate for you. You may need cascaded a lot of properties like this one. This one requires shifting, scaling, and then integration to come up with those triangular shapes. That is equal to 1 over t. It's from the formula. X of t e to the 0 dt within one period from 0 to t, which is the area under x of t normalized by the period. Now another a little bit more interesting question. Our signal x of t is an impulse train. On the t-axis that are separated by a period of capital T. Like this. It's an interesting signal, but yet it is periodic. Therefore, it must have Fourier series coefficients. First, let's not do anything about that. Let's find the Fourier series coefficients of this impulse train. By the way, the mathematical representation or notation of this impulse train is this. K from minus infinity to infinity. Always remember this. Delta t minus k times capital T. So if I give you an expression like this in a more mathematical form, you should be able to visualize it first and see that it corresponds to an impulse train. So what are the Fourier series coefficients of this impulse train? And the best way to find these Fourier series coefficients is directly using the formula. Because inside the integral, we have, within one period, we have impulses. Inside one period from here to here, there is only a single impulse in the center. That is delta t, e to the minus j k omega 0 t dt. And look at that. Because of the impulse, this thing is valid, or it scales only at t is equal to 0. At points different than 0, delta t is 0, therefore you don't multiply with anything. Impulse only picks one sample of this e to the minus jk omega 0 t, and that sample is the point where t is equal to 0, the center. When t is equal to 0, what is e to the minus jk omega 0 t? 1. So that is equivalent to saying 1. And then we have delta t times 1. When you integrate delta t, when you integrate the impulse, what is the area under the impulse? What was the area under the impulse? 1. Which says that ak is equal to 1 over capital T times 1. And that's a very bad signal, because it is not decreasing in magnitude with larger k's. For all k's, the Fourier series coefficient is always the coefficient is always 1 over capital T. It has the same value. So, by the way, using these Fourier series coefficients in the reverse question, if I give you this, what is the time domain signal corresponding to that? From here, the time domain signal is x of t is equal to summation k from minus infinity to infinity ak, which is 1 over capital T, times the corresponding harmonic. What was that? E to the plus jk omega 0 t. Omega 0 is 2 pi over capital T. So maybe I should write it like that. Jk 2 pi over capital T t. And the formula claims that it's equal to 1 over t summation k from minus infinity to infinity e to the j k 2 pi over capital T t. However, we also know that x of t was this. So let's also write that k from minus infinity to infinity delta t minus k capital T. Now one of the things that I have most difficulty in understanding is the equality of these two. How come a sum of complex exponentials is equal to a sum of impulses? Sum of complex exponentials are smooth sinusoids, and by adding up those smooth sinusoids, I come up with infinitely many impulses. An impulse train, as the name implies. A train of impulses. Interesting. And this is a way to prove it. It was again, I haven't seen it, but afterwards I have seen it in mathematical proof books. This is something mathematical. The proof was asking this. Prove that the left-hand side is equal to the right-hand side. Using mathematics. Can you prove it? Well, the proof requires the knowledge of Fourier theory, as you see. These two are equivalent, so the proof is complete. Interesting. Anyway, so these are the Fourier series coefficients, all 1 over capital T. Now from there, can we, I'm going to leave it as exercises, but you will find the answer in the book. Before finding the answer in the book, please try to do that. The exercise is as follows. Verify the equality of these formulas. What are the Fourier series coefficients of the well-known pulse train? You may ask you this question, what do you mean by that? We have already found it. Suppose this is g of t from minus t1 to t1 with a period of capital T, and this is capital T over 2. Therefore, we have already found the Fourier series coefficients of this one, right? We know it. Now find the same Fourier series coefficient formula, this time starting from the derivative of g of t. What is the derivative of g of t? Let's call it g prime of t. G prime of t is, if this is 1, the derivative of a unit step, 1 magnitude step increase, its derivative corresponds to a unit impulse. Because the integration of that unit impulse will give you 1 afterwards. So the derivative will look like this. An impulse at minus t1 with magnitude 1. Again here, another impulse. Here, another impulse. So this will, the higher going places will have derivatives corresponding to this one with a period of capital T, not T1, capital T. But of course, it also has the downward going places. The downward going place is from 1 back to 0, and it's again a unit impulse with magnitude -1. In order to be more precise, I'm going to draw them with red as downward going arrows. And by the way, the period of those red signals is also capital T. Okay. So now what do we have here as the derivative signal? We have a combination of two impulse trains. First the black ones, the upper ones, with a period capital T. Then the red ones, the downward ones, they are also with period capital T. So what are you going to do? You will find the Fourier series coefficients of these black impulses and red impulses. And the Fourier series coefficients will be extracted from the Fourier series coefficients of this impulse train, which are all 1 over T here. But of course, the Fourier series coefficients of these black signals is not 1 over T. Why? Because it is shifted towards left by an amount of T1. And do you know what happens when you shift something? You multiply with a complex exponential. Do that. Multiply with a complex exponential and find the Fourier series coefficients of the black impulse train. Then for the white impulse train, it is minus, it is negated. So the Fourier series coefficients are of course negated. And then shift it towards right. By shifting towards right, this time you will multiply again with another complex exponential. Okay? So two complex exponential multiplied terms of 1 over T. Then what are you going to do? You are going to combine them, add them up, because they have the same periods. And you come up with the Fourier series coefficients of G prime of T, and let's call it BK. It's complicated. It's not very difficult, but it requires some effort, some algebraic effort to derive that. Once you find BKs, then what is the next step to find the Fourier series coefficients of the top one? The top one would correspond to the integral of the bottom shape, because the bottom is the derivative. So you have to multiply it by 1 over jk omega 0. And you will achieve the Fourier series coefficients of the top shape. Make sure that what you get is the same as the original observation, the original answer that we gave to the first example, because this top shape was the first example. And we already know its Fourier series coefficients. Are they the same? That would be a verification from a completely different path to come up with the same expression. And I can clearly see that they would be the same. Why can I clearly see that? Because 1 over T are Fourier series coefficients of these ones, and you have to multiply with a complex exponential with a negative complex exponential, e to the minus jk omega 0 sort of thing. E to the minus jk omega 0 t1. For the other one, it will be a positive thing, positive shift, so it will be e to the plus jk omega 0 t1, because this shift is t1. So one exponential term is positive, one exponential term is negative. And one of them is positively signed, the other one is negatively signed. It will generate a sign. But there is no 1 over 2j yet. That 1 over 2j will come from the integration. After the integration, there will be 1 over 2j k pi. And if you check the answer of this first question, you will see that there was a sine something divided by k pi. That k pi is already coming from that integration. Probably you will be able to do that. Just do it as an exercise to make sure that you have the necessary skills to apply the properties. This one.
Biz kosinüsün Fourier serisi olarak yazarken sadece iki tane vardı.
Yes.
Mesela burada impuls'ı sağa sola üstünü kaydırırken eşitliğin sol tarafı, en son bir eşitlik yazmıştım. Bir tane biri impuls.
This one?
Evet, orada 1 bölü t değil de 1 olması daha mantıklı olan sürekli birler var yani her tarafta.
No, unfortunately not. From the formula, it comes this way. It's a normalized periodic sinusoid, summation of infinitely many periodic sinusoids that gives you impulses. This is the correct formula.
Peki bir şey daha sorsam. Yukarıda biz AK'yı bulurken direkt impuls respansın şeyine integraline nasıl integraline bir dedik ya.
Yes.
Orada T gibi bir değer elde etmez miyiz acaba?
No, why?
Bir ya. Yani orası direkt impulslarla bir olarak kabul etmişti.
The area, this becomes one. Do you agree with that? The top one. And then we only have integral of an impulse. The area under the impulse. And by definition, the area under the impulse is 1. It is defined to be that way. It's a unit area pulse that is made arbitrarily narrow and arbitrarily tall in such a way that the width and the height multiplied will give you always 1. That is the definition of an impulse. It's not a physical signal. It has a mathematical definition saying that the area under the impulse is 1. And of course, if you're integrating, there will be no t term anyway. Even if this is the top thing is a very complicated, it may be a very complicated time function. If you integrate from a limit to another limit, there will be no t variable after the integration. Because you have integrated, the time is gone after the integration. No matter how complicated it may be. This one is not very complicated, it is simple. But even without this simplicity, a time function integrated will give you something independent from time. It may be parameterized in terms of frequency, it may be parameterized in terms of something else, k for example, but it is never in terms of t. It can't be, because it's integrated by dt. If you don't see that, we can talk about that later, if you still don't see that. Now, we have a last example for today and for this first period before the examination. And it's the difference between the concept of measurement in science and the concept of measurement that you have learned in high school. Now, the measurements that we learn in primary school, high school, even in the university, is by using a measurement tool, which is usually physically quite an obvious element, like a ruler. With a ruler, we measure something, and we say it is 1 centimeter long. That's much. Unfortunately, in many cases in science, measurement also requires computation. It's not an immediate observation from something. What you observe are, in many cases, especially in electrical engineering, in many cases some voltage values that are garbage. You get some garbage observations. From those garbage observations, what you are trying to do is, by computation, you must reconstruct the data that I'm looking for. Has any of you ever been to computed tomography, CT tomography? Did you ever have your tomography taken? Good. I'm glad none of you have ever, because it's not something very good. But what it gives you as it gives you an image, by the way. The computer tomography image is an image, but that image is not like a photography. It's not captured from a camera. It's an image that is constructed to show you a slice of you. They cut your belly, and then they look at that. And in your slice of your belly, you have your stomach, liver, and all those tissues and things like that. Now, how can you take that image? Are we going to cut you and capture the image from there? Of course not. What they do is an indirect methodology. They take X-rays from several angles around your belly. From this angle, an image, another angle, an image. From several angles, it actually rotates around you eventually. And then from those several X-ray images, you must make a computation to combine them and to extract an information of your inside slice image. It is constructed. In many cases, that is the way that you make measurement. The measurement corresponds to the computation as well. For instance, the Hubble telescope, there was a telescope that was sent to the space, and they realized that it has some optical errors several years ago when it was first launched. Very expensive experiment. But the optics were flawed, so the images that it acquires from deep space are garbage. And what they did is they corrected it from the Earth, from the base down in the Earth, down on the Earth. They inverted, they found the amount of distortion that it applies, and they tried to invert the system of that distortion to come up with the sharper image. So they said, we fixed it. They fixed it mathematically, of course. They didn't go to the space and somebody just fixed it over there. It was a very expensive, that would be very expensive to go and try to fix it. So the measurements also require computations, and we will see an example of a measurement in an indirect way to come up or to extract the signal, to measure the signal. And instead of measuring the signal by itself, we just observe some side information from them. And the side information are listed as follows. We know that the signal is real. By the way, this needs not be a measurement or an observation. We know that it is real. It's a side information. We may also use those informations to compute the measurements. So we know that the signal is real, and we know that it is periodic. We made a measurement, but we could also only measure its period. So we observed that it is periodic with period equals 4, which immediately implies that it has Fourier series coefficients, AKs. But we couldn't observe the signal itself still. We have another information. We observed it to be band limited. In other words, for k greater than 1 or less than minus 1. In magnitude it is greater than 1, in other words. It's equal to 0, but we don't know what it is. For k is equal to minus 1, 0, and 1. Therefore, it has only 3 harmonics. One of them is the DC, the other two are the 2 harmonics. Now, even with this much information, we start seeing that it consists of a sinusoid, a pure sinusoid, a cosine or a sine or a shifted version of that. Only then we will have A1 and A minus 1. If you have A1 and A minus 1, it is either a sine or a cosine, or cosine omega 0 t plus a theta, an amount of shift, which we don't know. We couldn't observe this shift yet. What else do we observe? we observe a reflection of that. Suppose that you have a mirror, and from that mirror we are observing something, and that reflection is observed to be an odd signal, such that the Fourier series coefficients of these y's are bk's that are connected to ak's with this formula, e to the minus j pi k over 2 times ak. So y of t has a link to our x of t using this. Can you see that y of t corresponds to a shifted version of x of t? Because bk is an exponential term multiplied by ak. So y of t is the shifted version. We couldn't observe x, but we could observe somehow a shifted version of that. And we know that it's an odd signal. What's an odd signal with two coefficients? With two Fourier series coefficients? It's a sine. The only odd signal with two Fourier series coefficients is a sine. So y is a sine, and it corresponds to the shifted version of x. And we also measure the power to be equal to 1 over 2. If the power is 1 over 2, then it means the sinusoid, if there is no DC, we don't know whether there is no DC or not yet. If the power is 1 over 2 and if there is no DC, then it must be a unit sinusoid. 1 times cosine or 1 times sine or something like that. Now let me ask you this. From 4, we say that by shifting a sinusoid plus DC, we obtain something odd. Can you obtain something odd by shifting something like this? Let's say it's a cosine. So this is the amount of DC. The DC is not 0, in other words. It's shifted upwards. By shifting this to make a sine, can you make an odd signal? Can you make a sine? No, you cannot. Because if there is a DC component, then it will be like this. Right? Something like that. Is this an odd signal? No, it's not. No, it's not an odd signal. An odd signal cannot have a DC component. Do you agree with that? If there is a DC component of a periodic signal, then that signal cannot be an odd signal. What is an odd signal? An odd signal says that by flipping around the origin, that would correspond to the negative of itself. What is the negative of this? The negative of it, let me draw by red, would be something like this. Right? And red is not the negative of the negative of black. So this is a good and critical information. An odd signal must have no DC, which says that there is no A0. The DC is 0. Previously, from the information, we already know that AK is valid for k is equal to minus 1, 0, and 1. And now we only discovered that it is there is no A0. It is only for k is equal to minus 1 and 1. And then from 4 we need to measure how much shift it corresponds to. Excuse me, in the question I have miswritten something. This bk is not only a shift, as I said before, but there is also something else. There's a minus k. So bk is equal to e to the minus jk over 2 times a minus k. And that a minus k means the mirror, the flipped around version of x, and then shift. What does this whole thing correspond to? Let me write it again here, because I'm running out of space. bk is equal to e to the minus j pi k over 2 a minus k. First of all, a minus k, so x of t and y of t are related like this. Due to a minus k, y of t is equal to x of minus t with a shift. And the shift, the amount of shift is, how much is that? 2 pi k over 4 is already the frequency. T0 is how much? What is T0 here? Minus 1. So this is the relation between y of t and x of t. And this is a sine wave, because it is odd, with 2 coefficients only. And it's inverted, and one shifted version of it would correspond to a cosine wave, whose magnitude is 1 from the power expression, from property number 5 here. The power is 1 over 2, so therefore it's a unit magnitude cosine wave with period, or with fundamental frequency of 2 pi over 4 or pi over 2, and that would make x of t to be equal to cosine 2 pi over 4 t with a plus or minus sign. And that's it. We can write it like this: plus or minus cosine pi t over 2. So this simple cosine is the thing that we are trying to observe. Very indirectly, with only 5 observations, 5 indirect observations, we came up to this. Why did I put a plus or minus? Because I don't know whether it's a plus cosine or a minus cosine. I only know its magnitude to be equal to 1. And I know that it's a cosine, but I don't know its sign, whether it's a plus, a positive, or a negative. So we determine up to a sign. Well, that is usually the case, because most of the recording equipments don't record negative intensities. The negative and positive cycles are always recorded with a positive. That's why we couldn't record, for example, for this signal. We just recorded something from the mirror, some reflection, some powers. We know it's a pure sinusoid, we know its period. And from that much information, we could only retrieve the signal up to a sign. X of t is plus or minus cosine pi t over 2. What does this say? It says that if I give you some information about a signal, can you reconstruct the signal? Could be a question. This is one example of that. And this example is also available in the book. Please check it out. Please follow the steps in the book as well. Most of the material are already found in the book, so whatever you miss, you may either rerun the videos, or you may run, or you may consult the book. So this is the last. This was the last lecture before the exam. Do you have any questions regarding the exam? Not next week, but the week after that. I don't know the date. I don't know when the exam will be. Is it available? Do we know it? Okay. So we will communicate anyway.